Street Physics.
Let's investigate our permanent magnet a little more closely, and just talk about what it is again. So basically, this thing is just a hunk of iron, and it just has a north and a south and an N and an S stamped in it. That's all it is. Now, is this actually the North Pole of a magnet and this is the South Pole of a magnet? Certainly when it was manufactured, right when it was made, it wasn't. When it came out of the smelter or whatever they do, I'm not really up on my metallurgy. It wasn't. But then they magnetized it. And if you take a look, here I have a compass, and if we take a look, the red portion of the compass needle, always the one that's marked is going to be north. So in this case, it's marked red. They may be different colors. It's got a dot on it.
What? What is going
on? I have the North Pole of a magnet, and it's attracted to the North Pole on the compass. What is going on there, right? And I can definitely see that the South is attracted to South. Well, that's because I messed with this hunk of metal. Basically, what they do when they make these magnets is you got a hunk of metal. They got some sort of machine, and I have one right here. This is a magnetizer. And what you do is you can see it's got north and south. What it does is it creates a magnetic field that's going to loop around. You're going to take this and let's see. North is supposed to go in first, so I'm going to put north in. And then I'm going to take another hunk of steel. If I was at school, I would grab another magnet, but I only have one. And here's a little Allen wrench. It's made out of steel, so mostly iron. And then I'm going to take another hunk of metal and put it over the top. And what I've done here is now I have a path for the magnetic flux, the magnetic field, to flow through a continuous iron path. And I turn this on. And what this is going to do, since it says coils in it, it's going to create a large magnetic field, which is going to magnetize the iron, okay? So that should have magnetized the iron. I'll take this off, and we'll take that off, and let's see how we did. So hopefully I put it in correctly. So now when I take the south end of the magnet near the compass, the north end of the compass is attracted to it, as it should. And when I flip it around, the north end of the magnet is attracted to the south end of the compass, as it should. I had it backwards before, so watch, I'll do it again. Let me make it backwards. So in this case, I'm going to take it and I'm supposed to put the north side down. I'm going to put the south side down. This is going to reverse the polarity of the magnet. Boom. Put that on there. So I have a nice path to go on, and I hit it, and it just sent a magnetic field through there. I'll do it a couple times. Let's take that off. All right. So now, if I put this here, this should be backwards now. And indeed it is. North is attracted to north, and south is attracted to south, because that's not really south. That is north, even though it's stamped with an S. Can't believe everything you read, right? Unless it's on the interweb. Everything on the interweb is true. So other than the interweb, you can't believe everything you read. You can't believe everything you read. Let's get this back the right way again. We don't want confusing anybody. North is down. Boom. Let's magnetize this. Boom, boom, boom. All right. Yeah, there we go. So it looks like we're good. We got, this is marked south and it's attracted to the north side of the compass, and that's correct. And this is north side of the magnet, and it's attracted to the south side of the compass, so that's good. All right. So that's how they make these permanent magnets. They just a hunk of iron, and they stick it in a real big magnetic field, and the domains align, and they put other materials in the iron to make the domains more sticky. Neodymium is one of the ones they do to make them real sticky, so that they line up, and then we take the magnetic field away, they still remain pretty well aligned if you have what they call a hard magnetic material. So, all right, that's what's up with bar magnets. Whenever you see something like this, a coil of wire, here's another coil of wire. Here's one that I made, and here's another one I made. Whenever you see these coils of wire, you can bet it's about magnetism, that it's some sort of electrical device that is somehow involved with magnetism. It might be creating a magnet. It might be trying to catch a magnetic field. There's all different types of things that it could be doing, but there's going to be magnetism involved. That's why we coil things, because it allows us to concentrate magnetic fields. It also allows us to intercept magnetic fields, and we'll see why we'd want to do that later. Let me put this over here, and so coils are important. We wouldn't be able to generate electricity without them. We wouldn't have electrical motors without them. And so it's important we understand them and how is the magnetic field oriented in a coil, because the orientation of the magnetic field is going to indicate how it's going to react with its surroundings. So let's take a look. We're going to learn a new right-hand rule for the magnetic field in a coil. Now, another name for a coil is a solenoid. Probably a more formal name is a solenoid. So I'm going to use that term, solenoid. So this is a solenoid. And if you look closely, it's wrapped in a certain way. And you could see that this side of the wire is going under, and then it's wrapping around, and this side is going on top. And the way the right-hand rule in a solenoid works is I'm going to take my right hand, and in this case, I'm going to need to know the direction that the current is traveling in this. And what I'm going to do is, let's say, for instance, I have two batteries here. This is the positive end, and I'm going to connect that to this wire. And then I'll connect the negative end to the other side. That's right here, this black one. I'm not going to do that right now because I don't want to wear the battery out just yet. What you would do is, in this case, the way I have this connected, the current, this is the positive end, so the current's going to flow in this way. And what you want to do with a solenoid is your fingers will wrap in the direction that the current is flowing around the solenoid. So if I had this big one, if the current was going this way, I would wrap my fingers that way in the direction of the current. If it was going this way, I would wrap my fingers this way, and my thumb would indicate the direction of the magnetic field coming out of a solenoid. And the field in a solenoid looks just like the field in a bar magnet. So in this case, I have the current coming in here. So I'm going to have, so it's going to come in from behind like this. I'm going to put my hand like this, and my fingers are going to curl around like that. That means my thumb is pointing this way. So my thumb is pointing that way. So therefore, the magnetic field inside of this solenoid is going to go this way, and then it's going to wrap around like our bar magnets, it's important we understand what the field looks like in a bar magnet, and it's going to go that way. So the field out the end is going to be that way, and the field at this end is going to be inward. This one's going to be out, this one's going to be in, right? Because I knew the current was coming this way, and so I wrap my fingers, it's going to come around, I wrap my fingers in that direction, and my thumb's pointing that way, so the magnetic field is going to come out that way, right? So that means, and remember, your compass points in the direction of the magnetic field. So the field's coming out this side, it's going to loop around and come back in this side. So let's see if that makes sense. I'm going to use this side, the short end, because it's closer. I'm not going to get a real big field out of this particular solenoid because it doesn't have an iron core. If I wanted it bigger, I'd have an iron core. But the nice thing about it not having an iron core is that at this point it's not exhibiting any magnetism. All right, so let me connect this. And now I want you to take a moment to think. If the field is coming in on this side, what end of a bar magnet is that? Is that north or south? Right? So take a minute to figure that out.
Pause the video now.
All right, so we've got our compass. I'm going to connect the other end, turn this into a magnet. And okay, so it's definitely reacting. So let's see, what do we got? It looks like this short end is attracted to the north side of our compass, right? Definitely attracted to the north side of the compass. So therefore, what pole of a magnet must this be? Now, when I take it away, it's not a very strong magnet. You can see it's aligning with the Earth's magnetic field. But if I get it closer, there we go. So, what end of a bar magnet is that then if it's attracted to the north end of that compass? That's right, it's south. This is the south end of the magnet, and indeed the field does come into the south end of a magnet. So that is the right-hand rule for a solenoid. To use my bigger prop, the way it works, this is different than with a wire. With a solenoid, our fingers wrap in the direction the current's going. You know, the current's either going to go this way or it's going to go this way. So your fingers wrap in the direction of the current and your thumb points in the direction that the field is inside of this and is going to be coming out the end. So that's how you can tell what the direction of the magnetic field in a solenoid.
Extreme physics.